In this video, we're covering an important application of fields, finding the escape velocity. And as an added bonus, by the end of this video, you'll be able to answer questions like how small would I have to make the Earth in order to turn it into a black hole? So how would we go about figuring out the escape velocity? Well, not accounting for friction and air resistance, we could use our equation for the total energy of some object. That was explained in my previous video about orbital mechanics. The total energy is just equal to the kinetic energy plus the gravitational potential energy, which happens to be negative gmm over r. If you're unsure about why that is, I recommend you check out my video on orbits, or if you're familiar with calculus, my proof of the formula. In any case, we're going to very slightly change this equation because we're searching for the escape velocity from some body. So instead of using the distance between the center of masses of the two objects, we can just use the radius of the planet or star, which we're going to call capital R. It still looks like we have two unknowns here. We should already know the masses of the two objects and the radius of the planet, but we don't know what the total energy is or the escape velocity, which is literally what we're trying to find. Well, actually, if we define the escape velocity as the initial velocity that provides just the right amount of energy to get little m from R to very far away from big M, essentially to infinity, because we want to get out of the gravitational field of big M, then we know that by the quote-unquote end of the rocket's journey, its potential energy will be zero. And because we're looking for the absolute minimum possible velocity, we know that the kinetic energy would be zero by the end of the trip as well. So total energy is zero at the end of the trip. But by conservation of energy, that means the initial total energy was zero as well. Now we can rearrange to find the velocity. Add the potential energy to both sides, multiply by 2, divide by little m, and take the square root. There you go. That's the escape velocity. So what was I saying about black holes? Well, if I said that the escape velocity from some object was equal to the speed of light, what would the radius of that object be? Well, with some light rearranging that I'll leave you to do, we see that it should be 2 times the gravitational constant times the mass of the object divided by the speed of light squared. This radius has a special name. It's the Schwarzschild radius, the radius of an object at which the mass turns into a black hole, since not even light can escape from it. Let's try an example with Earth. Given that the mass of the Earth is 5.972 times 10 to the 24 kilograms, and some substitution of values, we find that some mad scientist would have to crush all the mass of the Earth into a region with a radius of basically 9 millimeters. So, thanks for watching. I hope you learned something useful. If you're interested in / need to learn more about orbital mechanics or are interested in seeing the derivations of some common results in physics, I've put up those for you to watch now as well. Thanks for watching. Bye-bye.